All right, so let's now look at the product property of square root here. All right, so to begin with the product property, let me bring up the observation that we've had after doing problem 3, part B, and part A together. So in part B of problem 3, this is what we had right here. So this is what we had in problem 3, the B right here. And so the work was done, and I explained the idea is as far as order of operations, then the group inside the square root right here needs to be done fast. So the answer came out, so 9 times 4 is 36. And we're taking square root of a 36, getting us 6 right here. And then as we advance, now we're looking back to part A of the example. I wrote down 2 separate square roots. Square root of 9 in products with square root of 4. So my explanation there was that according to order of operation, then we must do the 2 separate square roots first. So square root of 9, and then whatever that would be, that's giving me 3. Square root of 4, giving me 2. 3 times 2 equals 6. The observation I would like to point out now is that the 2 answers, 2 different ways of doing the work, and 2 numbers, 2 primary numbers being involved here, 9 and 4, 9 and 4, but the way we did the operations were completely different in the order. However, the answer came out exactly the same. And so in that way, we recognize the following, we recognize what's so-called a product property, and allow me to bring that on the computer screen right here. All right, so this is what the product property is stating right here. So for A and B being any two numbers that are non-negative, greater than or equal to 0, then the square root of the product A times B, this is like problem 3B right here, the square root of 9 and 4 right there, right? The product of 9 times 4, the square root of the product of 9 times 4 right there. So that product here, according to product's property, now we realize that, hey, the square root of A times B, right there, the square root of a product A times B equals to the 2 separate square roots multiplied together. Just like in this observation, I now notice that the square roots as a conclusion, square root of 9 times 4 equals to the 2 separate square roots, square root of 9 and square root of 4 multiplied together. And so we recognize that result, and then we realize that generality as a product property. And that is what is stated here in the product property right there. All right, and so after looking at the generality of the product property, a generalization of the product property right there, then allow me to bring in one problem so that I can show you how we can apply the product property into some real-time work right here. And then I call this a problem simply because it develops the idea, and then later on we're going to apply those ideas into doing different examples right there. Okay? All right, so in this problem, number 6 right here, allow me to show just a simple calculation problem. Now, notice, as far as a calculation problem, I don't have a calculator in front of me right here, and we have done some actual work with calculating with square roots earlier, and the number inside the square root here is different with the numbers inside of the square root in our earlier problems here. The number of the square root here is no longer a perfect square. You can see that 8 is not a perfect square. So unlike any of the problem I've done as examples earlier in this video lesson right here. And so here we unfortunately start looking at square root of those, calculating square roots of those numbers that are no longer perfect square. Okay, so how is product property useful in a problem like this? And so now for this problem right here, think about as far as the calculation. We cannot just rush into a calculator and punch it in square root of 8, which is going to give us a decimal. But so aside from that route right here, we have a better alternative. So we want to retain the exact nature of the answer. So this is what I realized. 8 itself on scratch work, 8 is a product of 4 times 2. So what I recognize here is that 4 is a perfect square and 2 is some number that's another factor that's a prime, being a prime factor. Okay, and then so 4 here is a perfect square. I realize that, and then 2 here is just simply some other number. So 8 on the other hand is understood as a product of 4 times 2. That means the same square root here can be calculated as square root of the products, the square root of the products 4 times 2. And so in that way, now the product property will kick in and be useful. We can now re-express this as, we can calculate this by doing this following. The square root property allows me to do one separate square root on 4 and one separate square root on 2 and multiply those together. And so now at least for us here, the square root of 4, since 4 is a perfect square, square root of 4 can be easily calculated as a 2 and then multiply. The other square root now is really, I mentioned earlier, this number 2 right here is a prime factor, and so it can no longer be square rooted. It can no longer be calculated with a square root, so we leave it the same. And this is now similar to one of the problems I've done earlier, that when we have an irreducible square root, a square root that can no longer be reduced, or a square root that can no longer be calculated, we leave that in exact expression. And then this final expression here is quite at that end for us. We have simply the square root, which is some value multiplied with 2. And then for even better way of writing it, we just write 2 square root of 2. But that's how we have written it. And so now the work I have done here is indeed for a problem like this. You will see that the kind of work here is commonly referred as, hey, if we cannot directly calculate and we don't want to calculate the square root to get a decimal, because the first problem in line here is the number inside the square root is a non-perfect square. And so if we cannot directly calculate, what we can do at least is to reduce. And so a lot of time later on, you will see that you will have a lot of problems where the problem instructing you to reduce the square root. Okay, so the idea is right there. At least if we cannot directly calculate to directly calculate and get a nice answer at the end, we can reduce the square root. And reduce here is in the sense that the final value, the final amount that stays inside the square root is smaller. It's smaller than 8. And of course, we have some values out here. And so now let's call that part A of the example, because I would like to bring in, with this problem number 6 right here, another problem. All right. And so here we clearly, let's think about, it's a different problem, even though I put that under this problem number 6 right here, part B, but let's think about in a different problem. Now we have a clear instruction that, hey, let's reduce the square root. And anyone with even the minimal amount of background can tell that this number here is not a perfect square. So calculating the square root for this is not going to turn out a nice looking value. And that's why there is that instruction that, hey, let's reduce the square root. So at least, once again, at least if we cannot get the exact answer, then we can at least reduce the square root. At least if we cannot get the nice looking final numerical value, then we can get the reduced square root. So here's how I'm seeing it. So very similar to what I've done in part A right here. It's all about, we look for a factor of this value that is being a perfect square. So here's again, I call this a problem simply. I just want to show the thought process so that eventually we can formulate a solid method so that we can start using that and so that later on I can demonstrate that repeatedly throughout the examples. Yeah. But so in this problem right here, here's how I'm seeing it. Learning from the experience of part A in the same problem, here's what I'm seeing. 720 can be understood as the product between 9 and 80. That's a start right there. Okay, 9 and 80. So I recognize a perfect square right here. So that will work. Okay, that will work. So think about, we have this, we can re-express this as a square root of 9 times 80. Okay, 9 times 80. And then, technically, I'm saying technically we could have, and then that will turn into a square root of 9 times a square root of 80, according to the product property. Okay, but then now at this point we're asking ourselves, are we happy with this root being the most final reduced roots yet? Because who knows, 80 could be having another factor as a perfect square that goes into that. And so think even a little further. And by the way, so the answer right here, yes, square root of 9, according to the order of operation, square root of 9 is a 3, and we have to multiply with square root of 80. But so back to what I was in the middle of saying, I was not feeling satisfied about how reduced this square root is. So I'm going to think even further. So the 80 itself right here is a product of a 4 times 20. All right, 4 times 20. And I'm not talking about the 3 anymore. I'm just now focusing on that 80, square root of 80. So my next step here is I'm reducing the square root of 80 right here. 3, that factor 3, we already found it there. And now existing between 3 and the square root here is a product. And so that equals 3 times square root. 80 is understood as a product of 4 and 20. And so I can apply the product property again. So I have a factor of 3 here is leaving untouched here. The square root of the product can be understood as square root of 4 times the square root of 20. All right. And so I can further apply, and so that makes it 3. And then what I was saying about applying, I'm going to apply to just apply the square root, understanding to calculate the square root of 4, making it to 2. So 3 times 2 times square root of 20. And so we are ending up with 6 times square root of 20. Okay. And then I'm still not, at this point, I thought I was done with the answer, but I'm still not quite convinced to myself about, or in other words, I'm not quite satisfied to myself in terms of how reduced this square root is, the square root of 20. So as another step, I am thinking about 20 as a product of 4 and 5. So this now, so in 20, we still have a perfect square factor and now with a prime factor. And so in my next step, from that earlier step right there, I reduced it down to the product of 6 and the square root of 20. But now 6, I'm going to leave it here. The square root of 20, I'm going to rewrite it as, I'm going to understand it as square root of 4 times 5. And one more time, I'm applying the product property. So think about this expression here as 6 times square root of 4 times square root of 5. All right. And so that gives me 6 times square root of 4 is a 2 times square root of 5. And the square root of 5 at this time, I am really satisfied because 5 itself is a prime number. So it can no longer be taken with the square root. So 6 times 2 is a 12. So my final answer here is a 12 times square root of 5. So at this point right here, I know that I'm done because the square root I have here, the only remaining square root I have here is a square root on a prime number, okay? Or at least later on, in other problems that it's a product of a number that no matter how you prime factorize it or no matter how you turn it into prime factors, it won't turn into a perfect square, okay? So we know we're done right here. But then the process is rather a little long here. I have to. The idea now is to look for a perfect square factor in your number so that you can reduce it. And so yes, we did reduce that every single step we do. But the process now all of a sudden produced too much work. So not too many viewers after viewing this, they love the idea of doing this. But now we can actually shorten down the entire process. We can shorten it down by one major important thing. So yes, we're still focusing on that central theme that we're looking for the perfect square factor, a perfect squared factor that goes into the number from start. But here's the idea. How about I would suggest, instead of just any perfect square, okay, we're not just looking for any perfect square. We're looking for the largest perfect square factor. So again, I repeat, yes, it's the main idea is it's about we're looking for a perfect square factor that goes into the number here as part of the product. But then now it's not just a perfect square factor. We're looking for the largest perfect square factor. Okay? And so what developed the idea here is that we saw that the entire work right here allowed me to erase the entire work and roll back to that beginning point. So right from that beginning point part right here, this is the way how I'm seeing it now. Yes, again, we are looking for a perfect square that goes into this product. But now we're not only just looking for any perfect square, we're looking for the largest perfect square as a factor of 720. So look for the largest perfect square. Okay, the largest perfect square that goes into 720, the number inside our root right here. as a factor. All right. And so in this case right here, my thinking process is the following. The largest prime factor I can find in 720. 9 was a perfect square factor, but it was not the perfect square factor. And then later, guys, we got only just the 4 and the 4s in each step that we go. So if we multiply all of those together, we actually end up with 144. It turns out to be the largest perfect square factor that goes into 720. And then you can see that the 144 is a perfect square of 12 like that. And so the other factor now is a prime. Okay. Now, yes, it will take some experience in order to arrive at the largest perfect square factor like that. Okay, but it takes some practice, but then at some point you will get fluent at that and get good at that. And so once we have found the largest perfect square factor that goes into this number right here, then we can rewrite the square root expression here as the square root of the product between 144 and 5. That's how I do that. And from this point on, I will stick with this method, this solid method, that we just look for the largest perfect square factor that goes into the number here as a factor. Now we only need to apply the product property once. So that makes it square root of 144 and multiply with square root of 5. In my next step, yes, according to the order of operation that we have done, we've seen how I demonstrated that with the earlier problems right there. Then we need to now take the two separate square roots. 144 will give us a nice looking value being a 12. The 5 right here is quite at the dead end right here, so we leave that as square root of 5. The problem comes out just 12 times square root of 5, or for short we write that 12 square root of 5. All right, so we have learned now a solid method that how we can use product property to effectively reduce the square root of a large number right there. What we're mainly looking for, is the largest perfect square that goes into 720, or that goes into the number in general as a factor. All right, so now we're stepping into problem number 7 right here, and the problem here that we have has a clear instruction. It's telling us to reduce the following expression. And then let's call this problem, this little problem right here, part A of the entire problem number 7 right here. But so, unlike problem 6 that we have done earlier, in this problem we're starting to learn how we can reduce a square root where there is an expression inside. We have an expression inside. Okay? And so in the way how I'm observing it, so the expression inside of the square root is a product of a numerical value and a power of some variable, and there's only one variable over here. But the idea is there's a product between a number and a group of variables, a product between a number and a group of variables. So with your algebra experience up to this point, you should be able to see that. So this is a product, right? And you should be able to see that 125, and I have explained that earlier. 125, let's take a look at that part separately right here. 125, the largest perfect square that goes into it is a 25. And the other value, the other prime factor is going to be a 5. Or the other factor, the other non-perfect square factor is a 5. So, and I have double checked and confirmed that this is the largest perfect square factor that goes into 125. So I'm rewriting this numerical value here as, and by the way, it's a square root. And so 125 is written as 25, the perfect square, times 5. Okay, times, now, another algebra experience, I can point out that from your algebra learning prior to this class right here, you can see that when it's in a complete product right here, we can handle the numerical part separately, and the thing about there's another part that you can, on just the variables, that we can just focus working on the variables. So the x to the 5th, I'm seeing this as x to the 4th times x. So your algebra experience, your learning from algebra should allow you to understand that power of 5th is the same as power of x to the power of the 4th to the x to the 4th power times x to the 1st power. There are many ways of doing that. Okay, there's x cubed times x squared, x squared times x cubed, which is essentially the same, right? Or x times x to the fourth. But I purposely chose this one. I chose this one simply because I see the x to the fourth specifically right here. I see the x to the fourth as x squared all squared, and that's another learning that you should have had from the previous course in algebra, and then multiply with the other x. So that means I see the x here as the largest perfect square factor that goes into this x to the fifth. Okay, and so in that way, I'm rewriting this as 25 times 5 times x squared all squared times x. So this first power here is irreducible according to some of the work that I've done earlier in the earlier problems right here. And now I can see this as the square root of, I'm going to purposely group out all of the perfect square values and expressions together. So 25 times x squared all squared, I'm grouping that together. And then times with the non-perfect square factors, I'm grouping them together as one group. And then from your previous learning in algebra, we understand that this 25 times x squared squared right here is the same as square root of 5 x squared all squared times 5x. And so now we have found, so really the 5x squared all squared is the largest. What I did here was just looking for the little perfect square, and together I grouped them into one big perfect square. So the largest perfect square in this entire expression here is the 5x squared all squared times 5x right there. So that's the thinking process, but that's, you see, but it spent me some time, right? And it takes your time to think through these things right here. And so the largest perfect square expression is a 5x squared all squared multiplied with 5x. So the same experience we've had, and I showed a little bit of reasoning how I led down to that, right? So now in the next step right here, the product property can be used in making that square root of 5x squared all squared times square root of 5x. And now taking the square root of a perfect square simply gives me 5x squared. And that 5x squared is going to multiply with the irreducible, the very irreducible 5x, because that can no longer be reduced. But that is now our final answer. And so before I close down entirely this particular problem right here, I want to mention, so the x to the fifth right here, and from how I recognize from the x to the fifth and be able to turn that into the product of the x squared all squared times x right here. The best thing to remember for anyone, when you see a power of x, say for example power 5 in our case right here, the power 5 of x, I'm just simply looking for the largest. What I looked for is, you see, I decided to turn that into x to the fourth times the power x right here. The square root, what we working with here is a square root. So what I was looking for here is I'm talking now among the powers of the variables. The powers of the variables. What I was looking for here is precisely was the largest multiple of 2 power, the largest multiple of 2. This is the largest multiple of 2. Okay, the largest multiple of 2. Less than 5. And so that's how I decided to come up with that 4. And that 4 can be expressed as, recognizing it as a multiple of 2 power, I always put that as a square, and then the other number come down because so here I got that 2 here simply because it's 4 divided by 2. Right? It's a multiple of 2, so we already had a 2 here, so it's a 2 multiple of 2. That's what a 4 is. All right, so let me bring in another problem. I call that part B of problem 7 right here to really enforce what we have learned from problem part A of the same problem 7 right here, and then we're gonna from here be able to see a solid method of how we can reduce an expression that has a coefficient, a numerical value, and in product with a whole bunch of variables to power and a whole bunch of variables to powers right here. So here I got 50 times a to the 7 times b to the 4th times c to the 5th. Right there inside the square root. All right, so once again, the main goal is just like that purpose we've had, that goal that we've solidified from problem 7 right here. We look for the largest perfect square. The largest perfect square inside of this that goes into this expression here entirely. But in order to do that for a problem that involves a crazy variables and products like this, let's break it down one by one. All right, so now I'm starting to get into recognizing the largest perfect square factor that goes into this entire product right here. Okay, and so I'm going to start out with the number. This numerical value right here, 50. The largest perfect square of 50 that goes into 50 as a factor is a 25, and the other factor is a 2. The other factor is a 2. And so in my square root now, the 50 is re-expressed as 25 times 2. Now let's advance over to that a to the 7. So a to the 7, the power here is odd. I'm going to look for the largest. So anytime the power is odd right here, I'm going to look for, and similar to part the A of the same problem here, I'm going to look for the largest multiple of 2 that's under 7. The largest multiple of 2 that's under 7. And so in this case right here, okay, the largest multiple of 2 under 7 is a 6, power 6. So I'm going to rewrite a to the 7 as a to the 6 times a. And this is a to the 1 power, by the way. And so I'm going to rewrite that a to the 7 as in product with a to the 6 times a. And so I have to also clarify, to give an extra clarification aside from what I've done back from part A right here. But we're not just, so we're looking for the largest multiple of 2 under a power, but now precisely we only do that. We're only doing that when we have odd power. Anytime we have an odd power in our variable power like that. So with this power here being an odd power for our variable, we look for that. Yes, we look for that largest multiple of 2 under 7, under this odd power. The reason I mentioned that because now the next variable here has power 4, which is itself already an even power. So I'm just going to leave that the same in product to a to the 4th. And then again, the next one here I got c to the 5th, which is an odd power. C to the 5th. I'm looking for the largest multiple of 2 under 5 here. That largest multiple of 2 is a 4. And I'm putting that as c to the 5th equals c to the 4th times c. And so now I can re-express that as c to the 4th times c. These factors and powers are all inside our square root expression. And now I'm going to rearrange these factors a little bit as a further step on my process to find the largest power of the perfect square factor over here. So large square root. This is a perfect square. It's a 5 square times 2. The a to the 6 right here, to see the perfect square out of that, it's going to be an a cubed square. So you can see that we intentionally found that largest multiple of 2, because once we recognize the multiple of 2 power over here, we're writing that as a square of a power, whatever multiple that is. So it's multiple 3 of the power 2. That's why I wrote it as a cubed square. And I'm timing a. Now this one right here, I'm seeing that as b square. And this one here, I'm seeing that as c square, and multiply with the last c like that. So now we have a lot of squares, perfect square like that. So we can regroup these, making it, now it's a square root. I have 5. Before I write down the square, I have a 5 a cubed times a b square times a c square. Okay, but all of those there is a square. So I just regroup these and put it all into one perfect square. That's how I got the 5, and then a cubed, and then b square, and then c square. And then all of that entire factor, that's in that entire product being a perfect square. And now I'm in product with, so now I have the non-perfect square here being grouped together. So 2a times c right there. This is the group of the product that's a non-perfect square. And so now the product property will kick in right here, will start being applied. And so I really hope that, and my aim for teaching this material is that I hope that at some near future, anyone viewing this lesson should be able to even skip these two and leave these two steps right here in your in your mental thinking process right here, in your thought process, instead of showing it out. So you just simply need to go straight from here to here, because the main goal, again, the main fundamental is to look for the largest perfect square factor that goes into the entire product here inside the square root. These are just thinking process that leading down to how we can find that right here. And I hope anyone viewing the lesson can someday speed up and even skip these, because you already had been able to arrive at this successfully. All right, but now the product property applies here for square root. We can have 5a cubed b squared c square r square as a separate square root, multiply with the square root of the irreducible non-perfect square 2ac. And so now, getting the square root of this is just exactly like the work we have done in some of the earlier examples and demonstration problems. So here it's coming out for us 5a cubed b squared c squared. And that entire expression here is free from the square root, and then it's in product with the square root of 2ac. All right, so that's how I have reduced the square root of an expression that has coefficient or a numerical value in products with those the various powers of the variables. All right, so we're getting into our first example, and right here in this example, we are asked to reduce this square root expression right here. And let's call that part A of the example. I do intend to give more than one problems in this one example right here. But so we have learned the fundamental method right here. So to reduce this square root, okay, and you can notice this number by itself is not a perfect square. So to reduce this, the fundamental we've learned throughout problem 7 and problem 8 is that we simply look for the largest perfect square. So just one last time, I'm showing the little thought process here, but the largest perfect square that goes into 50 is a 25, and the other non-perfect square factor is a 10. And like I said, this is already the largest. And how I can arrive at that so fast right here, think about the prime factorization process that arrives you there. Okay, and it takes experience to get to this. But so now square root of 25, square root of 250 is expressed as square root of the product between 25 and 10. And since 25 just earlier is stated to be the largest perfect square factor, now I can apply the product property, turning that into a square root of 25 in product with square root of 10. And so now we can easily calculate the square root of 25, making it 5 in product with square root of 10. And the best form of writing that, 5 square root of 10. All right, and so now another problem that I call part B in this example. Let's reduce, we are having the exact instruction right here. Let's reduce the square root of 72. And so now looking for the largest perfect square that goes into 72 as a factor. Here's how I'm seeing it. 72 is a product of 36 and 2. 36 times 2 makes 72. And this is a perfect square, and it seems like it's the largest one already, the largest perfect square already. And so now I can rewrite the square root of 72 as a square root of the product between 36 and 2. And so now product property allows me to write that as, to work with the problem as a product of two separate square roots. Square root of 36 times square root of 2. Order of operation now, according to this work, order of operation tells us, hey, we should calculate these two square roots first. So the 36 here, square root of that is a 6. The 2 here, square root of that is irreducible. So unless we go with the decimal value, so I'm leaving that exactly the same way. So it's 6 times square root of 2 in product. And so the better form of writing that, 6 square root 2. That's the final answer for that. All right, so for this problem here, in our example 5 here, we're asked to reduce this problem here. I call it part A of example 5. So we're asked to reduce the square root, but the square root here is similar to problem 7 that we've done earlier. It's a square root of a variable expression where we have 80 times x to the 5th times y squared times z cubed right here. But once again, the main fundamental the method here is we're looking for the largest perfect square that goes into the entire expression here as a factor, the largest perfect square as a factor of this. And so I have explained a lot in the video in the problem 7 earlier to show you how I can track down and decide the largest perfect square when it comes to variable all over here. So now once you've had that, hopefully you have some chance to practice on from what you've learned after viewing problem number 7. So here I'm just gonna get straight into that, the final largest perfect square. And just like I said, my aim is to have my viewers and supposedly my students learning from me is to be able to recognize the largest perfect square out of this expression in the fastest, in the least amount of time, like that. So here's how I'm seeing the perfect square factor over here. 4x squared y z all squared. That's the largest factor as a perfect square that goes into this entire expression. And then the remaining one will be 5x z, like that. All right, so what I've just now, I've skipped all of that step where I showed the thought process, because like I said, I showed the thought process and the thinking that led to the reason in the problem. Here I'm just applying that thought process right here, and so it really takes practice to get that quick to get here. So, but what I'm looking for mainly here is the largest perfect square that goes into the entire expression here as a factor. And so now that perfect square is here. It's the square of 4x squared yz. And now I can apply the square root property. It's a separate square root for the 4x squared yz all squared. I'm multiplying that with a separate square root on 5xz. And since the 5xz is so irreducible, in the next step it remains exactly the same. But this square root of a perfect square, we have done that we've learned experience from our earlier problems like that. We can just simply leave that as 4x squared yz, no more overall square. But that times the square root of 5xz. That is our final answer. All right, so allow me to bring in another problem in this example 5 right here. So we are asked to reduce the expression right here inside of our square root. And so unlike the earlier problem in example 5, here what we have here inside the root is a quotient, right? We did not really learn any any property on quotient. But what we can do here at least, now we have seen, I've demonstrated earlier within this lesson that according to order of operations, then everything that stays inside the root here needs to be done first. So what we have entirely inside the root here is a quotient. So without learning anything fancy, without learning anything advanced yet, then we can still do this. We must be able to simplify the rational expression inside the square root before we can take the square root. So let's do that, because according to order of operation, we can always finish out finish calculating the expression, the division, the quotient inside the root first, because that's all that here is grouped together. And so now I'm going to leave the square root here the same. See, 75 divided by 5 gives me 15. X to the 5th divided by x squared gives me x cubed. Z to the 7th divided by z to the 1st power reduces down to z to the 6th power. All right, and so now we have a final, a square root expression that we can start working like how we've done that in part A, or from the demonstration problem, the 7, like that. And so once again, now I can start doing all that usual work. So the first thing here in this problem here, we only got to a little slightly higher challenge right here, that we got to reduce the fraction here to arrive at one single thing right here. One single product of all just number and variables with powers and all that. And now we're going to start looking for the largest perfect square, the fact that goes into this expression here as a factor. All right, so it looks like 15 has the largest perfect square no other than just 1. So it's 1 times 15. So in other words, 15 itself is already quite at the dead end right here. It's not a perfect square itself, and we won't be able to find any the perfect square as a factor other than 1. Okay, so I'm going to leave 15 here the same. Z cubed, we can recognize some power as being a multiple of 2 right here, and z to the 6. So now the largest perfect square factor of this 15x cubed z to the 6 is going to be x z cubed all square right there. And then the non-perfect square factor is a 15x. So that's how I have recognized the largest perfect square as a factor, right, of this entire expression inside of our root that was here. And so now the property, the product property allows me to take the one separate square root on the xz cubed all square, and then that's in product with the irreducible square root 15x. And so now the final answer comes out simply x z cubed in product with 15x. That's how we're completed that work right there. All right, so now allow me to bring in problem number 8 right here, where after demonstrating a problem, we should be able to draw out some more generality in our learning, and then we can push into learning some more advanced stuff after this. So here we are simply asked to evaluate the square root of 5 all squared. Okay, and so to evaluate, think of the thought process right here. Now I'm bringing up things the way how I teach. I always bring in things that everybody knows without any advanced learning, and then from what we've learned right there, from what everybody knows, we're gonna start blending in what we're currently learning, and then so that we can come up with something more advanced. So the square here means the square of the square root of 5 right here means really we have the square root of 5 times or in square product with square root of 5. And I should have also mentioned that the idea is the square root of 5, the square root expression inside of the square here generally appears to be a very irreducible the square root expression. That's why the only thing we can write is we can understand that, hey, this square is the same as the two identical factors multiplied together. And so that's just that same algebra that you should have learned prior to entering this class already. And so now it turns out at this point when we get to this, it turns out that we can actually use the product property in the backward way right here. So on the computer screen, this is what we have seen earlier about the product property. According to the product property, taking the square root of a product equal to the product of two separate square roots. So we know that now. But just like what I said earlier, it turns out now that we can also think the opposite way around. That means now I can revise the product property a little bit. Now taking the product between the two square roots also turns out to be exactly the same as taking the square root of the product. All right, so this is easy enough to understand that logic. So now I am going to apply that logic in here. I'm using the product property in the backward way, in the opposite way right here, in the backward way. So now I can combine, I can take advantage of that product property, and now I can combine that into one square root of the two factors 5 and 5. So 5 times 5 is brought in together inside of one square root. And so now here's the usefulness. Here's the usefulness of doing this. It is now the square root of, so now once we have brought it into this, everything brought inside the square root right here, then we're talking about it's a square root of a product. So we have to, according to order of operation, we have to calculate the products first and then take the square root after. So now 5 times 5 gives me 25. So the work here is the square root of 25, which now gives it 5. Square root of 25 is a 5. Easy, just that. But so now, right from that problem that we've just finished right here, we recognize one thing. So it looks like here's how I'm done. I should have explained a little further as a step right here that the square root of 25 is a square root of 5 squared. The 25 itself is a 5 squared. So along that way, I drew out another generality. Right here from this problem right here, I can see it was a square root then being square. A square root expression then being square. It turns out that see, It all has been equal, and it should have also been equal to the square root of this perfect square of 5, and then lead to the final answer equal 5. And so it should be equal to square root of the 5 square. So I bring that square inside. So what I'm saying now is that here I have the order of operation says take square root then square, but that operation is the same. Will give you the same answer, equal value as square the number, then take the square root. Square the number first, then take the square root. I'm using my word with the order of operation for you to follow along with them. Okay, so now right after this demonstration problem right here, let me bring in two little remarks right here. One remark to understand is that the property that we originally learned can now be also used in the opposite way, meaning we can, the same product property, we can also use that in a way that, hey, we can combine the product of two square root into a square root, the square root of a product. So that's one remark. And another remark that we can find stating that, hey, for any value a that's non-negative, greater than or equal to 0, then see, taking the square, so back connecting this to our problem number 8 that we've just finished. The 5 right here, a right here is playing in the role of that 5 in our demonstration problem earlier. So square root of a all square, so taking the square root of a number and then square should turns out equal taking the square of a number then take the square root. So here the order of operation says the opposite way. We square the number and then we take the square root. But the two works here will come out equal answer. All right, so allow me to bring you into example number 6 right here. And so just now we have learned that the product property can be used in the backward direction, meaning we can go from a product of two square root expressions, can turn that into a square root or the square root of a product. Okay, and so utilizing that right here and here, and that has become a solid technique for us that we can use a lot. So allow me to just keep it one problem right here and make it simple according to the product property we've just now learned. So this product of two square roots, I can now write that as a square root of 5 of the product 5 times 45. The square root of 5 times 45. And so now with this, it turns out that this product, and at the point now is that once we have combined that, the order of operation is telling us, and we've done similar problem earlier, we don't want to go back to this, but we want to advance further, that we think about order of operation so that we can do we can calculate according to this product first. That's making it 225, and then we take the square root. And so now 225 now is gladly a perfect square. It's a perfect square of 15. And so now seeing that as a perfect square, taking the perfect square, the square root of a perfect square, I'm adding out into 15. And that's how we can utilize the product property in the backward way to do problem quite effectively like that. All right, and so here allow me to bring you into another example. So in this example, I want to apply I want to have a problem where we apply just directly that product property, but using in the backward direction right here. So the problem at start, we're given that the problem here as a product of two radical expression of two root expression right here. And this is why the problem here, you can see that the problem here as a worded instruction, it's instructing us to simplify this entire larger expression right here. It's a very large expression, so let's make it shorter. Okay, and so the most direct route right here, allow me to say that it's the most direct route, and then if you have time you can view my later notes in this video as I can explain how I can call it the most direct route. It means the route that takes the least step right here. Okay, or how about the route that takes the least steps right here. So the route that takes the least step to me here is which is directly combining these. So 1 square root, 12ab is going to be in product with 3a cubed b, but so that product now is inside the square root. All right, and so in this way right here, now we can order of operation is telling us, hey, let's really multiply these two expressions. So that means what? Inside the square root, we come up with the following. 12 times 3 algebraically will give 36. A times a cubed will give me a to the 4th power. And b times b will give me a b squared. And so now, after what that is, we're going to take the square root. So by far, the expression has become a lot simplified. See, by combining the two roots into one square root right here, we have reduced the number of times that we can do square root right there, and we brought it down. So think about this expression right here. It's a lot less operations compared to the beginning one, even though it will give out this exact same result right there. All right, and so now this work right here, the work that we have done in some of the earlier demonstration problems will come back in right here. All we look for is the perfect square, or the largest perfect square that goes inside of this expression. So I see that the expression itself is already a perfect square. So 36a to the 4th b squared is understood as 6a squared b all squared right there, and inside the square root. And so this is very similar to what we have done, what we have seen in the demonstration in some of the earlier problems right there. And so now the final answer comes out, 6a squared b. The expression here is even a lot simplified compared to the beginning version where it started with, and still a lot simpler than that because it has no more square root. It's completely gone, and a lot less operations involved. So this is the final expression. All right, and so now we're getting into the quotient property of square root right here. So now allow me to bring in the following observation. Now let's start out with a simple calculation problem that we have done, or we can do similar to what we have done right here. All right, so how about the observation I'm about to point out here? Just think about, let's take the square root of 100 over 36. Let's just calculate or evaluate or take the square root of 100 over 36. Okay, so this is things that we've learned right here. We can just apply the learning that we've had. This fraction inside of the square root, let's not worry about that as a quotient or whatsoever. Yes, it's a quotient, but let's not get to it. Right now, see that simply as a fraction. So this fraction here, 100 over 36, I can recognize and think about, we roll back to that point that we're only learn some very basic and with minimal amount of understanding. And so the square root, the fraction as a division here exists inside of the square root. That means we have to do things with that. So 100 over 36 is understood as 10 over 6 all square. 10 over 6 all square. So 100 over 36 is a perfect square of 10 over 6. And so in that way, I can further see that, yes, I can just simply take the square root of a perfect square with common thing that we have learned, okay, with minimal understanding. So now that makes it 10 out of 6. So that's about the answer. That's the answer of the square root of 100 over 36. And that's about the end of the problem for us. So, but now just think about, let's bring back the result that we've done from problem 4 here. Among problem 4 that I've demonstrated a few problems here. We had a problem like this. It was a square root of 100 divided by a square root of 36. Now in that problem number 4 there, okay, let's compare the results now. So this was from problem number 4. In that problem, I treated the problem completely as something that relies strictly on order of operation. So based on the order of operations, it's a division here, and we were dividing a square root by another square root. So we are required to do 2 separate square roots first according to the order of operations, because square root has higher order of operation, the priority, compared to the division. So that means what? Square root of 100 need to be done first. That's giving me 10. And square root of 36 at the same time. So these 2 square roots are supposed to be taken at the same time. Square root of 36 is a 6. So that's, and then we do the division, 10 divided by 6. But so now putting the 2 results together, we realize, hey, wait a minute. This answer is exactly the same with that other answer. This answer came from where we put the square root. See, here we had the square root of 100. square root of 100 over 36. The 100 over 36 is inside as a division, as a quotient inside the root. Here it's two separate square roots. Square root of 100 divided by square root of 36. So we drew out this important the conclusion right from this observation right here. So this came from problem 4. This is a problem I brought up right here. We have square root of the quotient 100 over 6 equals exact value with the quotient of the two square roots, 100 over square root of 36, 100 over square root of 36. So this is the beginning of what quotient property is all about. All right, so on my computer screen here, let's look at the statement for the quotient property. So the quotient property is stating that for A being a number that's non-negative, and for B, see B is the number that's, in any case, it's in the denominator, so it needs to be a number that's strictly positive because the denominator cannot equal 0. So again, for A being a non-negative value and B being a strictly positive value, then the square root of a quotient A over B, the square root of a fraction A over B, equals to the quotient between square root of A and square root of B, or it's a fraction where numerator is square root of A over the denominator is square root of B. All right, so we can directly apply the quotient property that we've just now learned into some very basic evaluation problem. Now, you see, I'm talking about, yes, for a problem like this as a little bit of a reasoning that leads to why I chose showing this problem right here as an example. Just think about it right here. Without the quotient property that we've learned, we can still solve this problem. So according to work that we've done in earlier demonstration problems, we can think of 121 over 16 as a 11 over 4 all squared. So we can recognize that 121 over 16 as a perfect square of 11 over 4. Okay, and then easily get the answer being 11 over 4. So some viewers already probably may feel impatient that I'm doing things that you already know how to handle. The idea now is different. The idea is there could be time, believe me, no matter, and it happened to me too, no matter how fast you are at recognizing a perfect square, there will be times things become challenging. So think about you are among those that this fraction doesn't come immediately in your mind as a perfect square. So this fraction 121 over 16 does not appear in your mind immediately as a perfect square. You have an alternative. The idea is we have an alternative. So we don't always have to crank through seeing that as a perfect square of a fraction. But if without seeing that as a perfect square, you can do the following. We make that square root of 121 divided by square root of 16. So now I just straightforward just directly apply the quotient property. And so now breaking it down into the separate square root, it will go hopefully a little easier for us. So now once you spent time through that little process right here, now all of a sudden we realize, hey, 121 is a perfect square of 11. So 11 square right here. And then 16 in the denominator is a 4 square. So now these are two perfect square. So square root of, and still the point now is that once we have turned that into the quotient of the square root right here, then order of operations here will continue on and hopefully get the problem done more easily, even though it's probably takes some more steps, but more solid. So in the numerator, the square root of 11 square gives me 11. The square root of 4 square in the denominator here gives me a 4. We have come to that. So that is our answer to this example. Nice and easy. Okay. Now I could have also clarified further. Now I'm talking about there could be time that you're unsure. There could be time that your algebra from the past course is faded away. So even though you recognize 121 is a perfect square of 11 and 16 is a perfect square of 4, even though you know so, you're still unsure. Think about, when we come to a class right here, the background in math is it's not always the same among everyone who's learning. Okay, and so there are the people who are still unsure about a perfect square over a perfect square. We can turn that into an 11 all over 4 all square. See, so without that option right here, you can still do this. All right, so in this example 9 right here, allow me to once again show another example where we can directly apply the quotient property on taking square root right here. So here we're taking square root of the equation 49x to the 6 over y to the 4th z to the 8 right here. All right, so now directly applying the quotient property, here's what we arrive at. What I have here is we have the square root of a quotient. And so the quotient property says that we can do two separate square roots. One square root is for the 49x to the 6. And then now we divide it by the square root of the denominator, which appeared to be y to the 4th, z to the 8th. All right, so that's how I used directly the product, the quotient property. And so now from that point on, now according to the order of operation, I can easily handle each one of these roots right here separately, and then in the end we put the two results here as one fraction, as one quotient. We take the quotient between the final square root. All right, and so for the first square root here, I can easily see the 49x to the 6 here as a perfect square of 7x cubed all squared. And then for the square root in the denominator, the part inside of that, the expression inside of that, I can easily see that as the perfect square of y square z to the 4th power all squared. All right, and now after taking two separate square roots, the one on top gives me 7x cubed. The one in the denominator gives me y squared z to the 4th. And that is our final answer. And so this is how we're done with the problem in number 9 right here. I just directly apply the quotient property. But now allow me to mention a little bit before we completely move away from this example 9 right here. If you follow the video lesson here closely enough, you can see that I'm using the exact same problem that we have done already in some of our earlier the examples or demonstration problems. So the idea now, I just want to point out, there are always the same problem and the same instruction. We want to simplify that earlier problem where I brought up the exact same math expression right here. The other problem, it was also we were also instructed to simplify. And so the approach I used earlier in the lecture was I see the entire quotient here as a perfect square of 7x cubed over y squared z to the 4th, and it's a perfect square of all that. And then we take the square root of a perfect square, which gives us that answer. But see, that route that we used earlier in the earlier demonstration problem or example may not be comfortable for somebody. That route may not be comfortable for somebody because when it gets pretty intense into a bunch of variables involved and numbers and all that crazy thing right there, it's starting to get hard. It's starting to get complicated, hard for someone or for a lot of people to recognize the entire quotient here as a perfect square. So that's why knowing the quotient properties here, the quotient property here will be extremely beneficial. So we can tackle it right down and separate that into smaller roots right here and handle each root a little bit more directly and then put them back. So yes, admittedly it takes more steps here, but then it takes less worry about whether we have arrived at the correct the correct perfect square or not. Okay, so it's less steps to write here, but it takes a lot of thinking process, whereas here we just go through the steps, but each step here is easier to handle for us. All right. All right, so now allow me to bring in problem number 9 right here, where I can demonstrate the idea, and then from that idea we can come up with some generalization right there. Okay, some generality. So here we're asked, in this problem, we're asked to evaluate, simply just evaluate this expression right here. So what I can see here is I have square root of 605 and divide that as a quotient by square root of 5. All right, so now think about without any advanced understanding. I've been saying from the beginning of our lesson that this here, according to order of operation, we have to calculate the one on top first and calculate the one at the bottom and then divide out. Unfortunately, that route, that direction is not working so well because the square root of 5 in the denominator is a very irreducible square root. And the square root here is going to be a large one, and it's not a perfect square immediately that's catching my attention. But then if we spend time searching for the largest perfect square that goes into 605 as a factor right here, it takes some time too. And so now as it turns out, that from this problem that I'm demonstrating here, now I'm starting to reveal that truth here. The quotient property can be used backward. We can also use the quotient property backward. So it turns out this way, that's also true. From being the quotient of two square roots, we can combine that into one square root of the quotient between 605 and 5. Yes, so now I guarantee that to you that it turns out that this is also true right here. Okay, so from the quotient property we have seen already, the backward way is also true. That means from the quotient of square root of a over square root of b, we can combine that, and that equals result with the square root of the quotient a over b, for a being a non-negative value and b has to be a strictly positive value. And so how is that useful in this problem right here? All right, I can see that 605, now combining that into one quotient. Now order of operation says you can go ahead and divide. Now 605 is divisible by 5 right there. And so we can easily divide 605 by 5 right there, making it, so now it's the square root of 121. Now that made it a lot easier to recognize. 121 is a square root, is a perfect square of 11. And so now the answer comes out easily, just 11. All right, and so just a little bit creatively use the quotient property, right? Backward, in the backward direction, we can make the problem, a lot easier to handle like that. Okay. And so now one more time, let me just show that quotient property that we're using in the backward direction again. So it's a revised version of our quotient property. For a being a non-negative value and b being a strictly positive value, square root of a over in quotient with square root of b should be able to be done as taking the square root of a over b. All right, so allow me to introduce example number 10 right here, where we're asked to simplify this expression right here. So this example is where I directly applied the quotient property where we used it in the backward direction right there. So we're starting out with, in our problem here, it's a quotient of two square root expression. Okay, so think about that. We don't want to separately reduce each of these square roots independently to cancel things out or to make it simplify. And so one direct route is that we can combine the square root using the quotient property in the backward direction. We combine it into one square root. And now I'm looking at 108 P7 Q3 over 3 P to the 5th Q. So this is now one quotient being inside of the square root. The order of operation now says, hey, let's simplify, and this is completely the reachable or doable for anyone. So without paying attention to the square root for now and only pay attention to the quotient inside of that, 108 reduces by 3, right? And that makes it 16. P to the 7 reduces with P5 right here, cancel out with P to the 5th, gives me P squared. Q to the 3rd power, cancel with Q right here, gives me Q squared. And these operations, the cancellation I've been showing right there, should be completely under your experience, your learning, that you should be able to understand. And so now we're taking the square root of that. So again, order of operation says we handle the quotient and then we take square root. So handling the quotient arrived us as 16 P squared Q squared. and then we take the square root. And so now this is easy to recognize, the part inside the square root. It's easy to recognize that as a 4 PQ R squared, and inside the square root. And so now we can easily see that as 4 PQ. And that is our final answer for this problem.